Hello everyone. This is Racy. I'm from National University of Singapore. I'm a PhD student in the computer science department, and today I want to share with you my learning notes on the ChatGPT training. So basically, I'm trying to demystify ChatGPT from a training perspective for beginners like me and maybe you. So let's get into it. So before I jump into any details, I want to share with you this great talk about the state of GPT by Microsoft Build. And I basically will walk through this great talk with their slides and try to add my explanations and examples to any of the things mentioned in there about how to train your GPT assistant. And you can watch the original video at this YouTube website. Alright, so as a beginner, I will go through the very basics of transformer basics, and then we will go into the details about the real training stages, including supervised fine-tuning for ChatGPT and similarly other large language models. And then we will go into the interesting part of RLHF, the reinforcement learning with human feedback. Then for part 4 and 5, I will talk more about other LLMs, including Llama, Palm, Vicuna, and we will do a short comparison between the different large language models. And last but not least, I will talk about some domain-specific large language models just to give you a hint about how these large language models have been applied to any of the fields like biomedical and chemical, cybersecurity, coding, and so many domains. Let's begin with the transformer basics. So if you're interested in this ChatGPT training, you may have already heard about transformer. So the transformer architecture is basically the thing shown on the right, and it composes of an encoder and a decoder. So what does that mean? It seems maybe a bit comprehensive to beginners. But let's just keep in mind that the input will always be a sequence of strings. That is, the input is the raw text strings. And first of all, you need to convert or transform your input raw text strings into embeddings. That is called the input embedding, which is a vector of shape, batch size, max sequence length, and embedding size. We will go into the details of how you get your embedding. But before that, let me just tell you more about the transformer basics, the important things. And the core of transformer is the attention mechanism, the self-attention. So the self-attention may sound like very complex, but it is essentially, to my understanding, a similarity matching between a given token and its context tokens through the query key value vectors. We will also go into that. And last but not least, the multi-head attention. That is just literally multiple attention heads in parallel. We will also go into that. So how do you convert your raw text to embeddings? For example, we want to have a vector of shape 14512 via embedding lookup, where 1 is the batch size, 4 is the max sequence length, and 512 is your embedding size. How do you achieve that? And this is achieved by tokenization. Tokenization transforms all text into one very long list of integers. But before we really get into the integers, let me just walk through the steps. You have your raw text, for example, this paragraph or this short sequence of text, and you do tokenize. You tokenize your raw text into tokens. For example, we know that in English we have words and characters, and we have this space in between words. So tokenization is similar to split the sequence by any spaces, or like comma, like period, but that's not that simple. We will split our raw text into different tokens or different parts. That could be, for example, for a word like this word tokenized, it could be further split into token and iced. And this is achieved by an algorithm called bipair encoding, or simply BPE. And for some typical numbers, we have like 10 to 100K possible tokens, and a token is roughly 3/3 of a word. So you can see that a word can be further split into tokens. But how do we achieve that? Let's move to the next slide. But before that, I will mention a little bit about the integers. So after you have your tokens, these tokens will be mapped to its index from a embedding lookup, or like you can think of it as a dictionary. So you have your dictionary of your input embeddings, word embeddings. So for each of the integer in this list, for example, this first 464 corresponding to this token the, this will be used to be searched against your embedding dictionary via the embedding lookup function, and it will return an embedding for this token. And in practice, we will just save this integer list to be used for the real functions in code. Why do we tokenize? Because the text can be long, but the number of unique words or characters from a corpus is limited. And there are other vocabulary words which can contain frequently occurring subparts. For example, you may see a word in your test set or at inference time that you never saw before. But this word can be essentially split into subtokens or subparts, which are already contained in your vocabulary from your corpus. So if we further split that unseen word by subparts, we can represent that word by the subparts, so that word's no longer something you never see. So therefore, we tokenize longer text into smaller linguistic pieces to reduce vocabulary size, and we help the model to grasp the syntactic and semantic relations between words, and we try to handle unseen words via subwords. And then we transform text data into numerical sequences to be fed into models. So this numerical sequences is essentially efficiently enhance memory usage, because numerical representations take less memory compared to raw text strings. And here's one simple example for tokenization. If we just want to tokenize this sentence, "I like tokenization," by BPE or your favorite tokenization algorithm, you can get "I like tokenization." And for more examples, you can visit this great Hugging Face tokenizers tutorials, which will give you more examples. So in terms of BPE, this is the Wikipedia page for the algorithm for BPE. And one thing about BPE is that it uses subword. So what is subwords? Subwords is basically every 2 bytes or every 2 characters that you look at, and you find the most frequent byte pairs. That's the so-called byte pair. And essentially, BPE is a data compression algorithm. And I just queried ChatGPT to give us an example of how BPE works. And let's see how it says. Q. Use BPE to tokenize tokenization. So ChatGPT tells us that let's assume we have already got a small BPE vocabulary. You don't need to worry about how this BPE vocabulary is built for now. Let's just assume we already have this BPE vocabulary with the following merge operations. Since this answer might contain some mistakes, I just crossed those lines that I don't think are correct. For the merge operations, we have the first rule: to and can become token. And let's also suppose these other merging operations are given. For example, T and O become to, and K and E and N become can, and this I, Z, A, T, I, O, N do some more merge operations will become ization. And then how this BPE works is like this. We have this tokenization, right? Let's see this example. I just put some space in between the characters to give you a sense. So when we write this way, we can look at every 2 characters, like every 2 bytes, and we find which bytes can be merged by these merging operations defined according to our BPE vocabulary. And here, according to the rules, the merging rules I just said, T and O will become 2, and KEN become KEN, IZA, TION become ization. And furthermore, we have this rule number 1 here. Then to and KEN will further become token. And now we have tokenization. There's no more merging rules. And this tokenization process will stop here. So, in a word, this tokenization will be split into subparts of token and ization. This is how we tokenize using BPE. So you may wonder how these merging rules, or what is this BPE vocabulary are built with. So this is the BPE algorithm. Just from my understanding, every byte pair you have the frequency for the occurrence of some pairs or like even longer characters, and you can, based on those occurrences, you can get the most frequent pairs or like this occurrences, and you specify the rules. For example, according to this algorithm here, you can have a rule of LO become low and LOW become low, and so on and so forth. And this is how you get your BPE merge operations learned from your dictionary from these words with their corresponding frequencies in your vocabulary. And to learn more merge operations, you can refer to this great paper, Neural Machine Translation of Rare Words with Subwords Units. All right. Now, let's suppose we already have our raw text converted to input embedding, and just one step further, we add the positional encoding to our input embedding that become the real input embedding before we feed into any of our transformer blocks. That is the self-attention blocks. So I will skip what this positional encoding is and why it is important for now. But let's just keep in mind that this is an important thing that you need to add to your input. So before we really get into the attention mechanism, I want to mention to you that this is the transformer architecture. But GPT is a decoder-only transformer that uses masked self-attention to predict next words based on probability. As you can see here, like the right part, this right architecture is the decoder. And to represent the current token, GPT utilizes its left context to compute dot product similarity that is normalized as softmax scores as attention weights over the given token's context. Then GPT will generate a contextualized embedding to represent the given token. That is the whole point of the attention mechanism, the self-attention, is to make a better representation for your input token. For example, for your current input token, you have already got your input embedding for that token, but you want a better one, a better representation. And you go through this self-attention, multi-head attention, and with all this residual connection, this feed-forward, norm, add operations, and you will basically represent this word by its context. So in that sense, let me give you a very quick example. So if you just use your static input embedding, that will be just one embedding. Even though you can learn, like if you're familiar with training or embedding updates, you can update your embeddings through training. But that's still very not specific to context. But if you are using your context to represent this word or this token, then you can get a different representation for a similar, like for the same word type every time, depending on your context. So if this word is polysemous, if this word has different meanings depending on its context, then this representation will be more flexible. So you will have a flexible, a contextualized embedding to represent this given word, which is better. And this illustration is taken from this great paper by Chris Manning. I suggest all of you read it. This is a really good paper. I benefit a lot from it. And this is basically what is transformer attention head and self-attention. So let's start from the leftmost figure. So for example, you have your input raw text, I went to the store, and currently we're looking at the token 2. And I just mentioned to you that each word or token, like this word 2, is converted to its input embeddings. But now let's just think about it, that each word can have its attributes. This 2 can have 3 different attributes called query, key, and value. And these are converted by matrix multiplication from its input embedding through some linear matrices of Q, K, and V. And for each word, you have 3 different vectors associated with it. That is the key value, the query value, and this value. And I'm sorry, this key vector, query vector, and your value vector. So let's see how these 3 attributes are actually used in the so-called self-attention. So now just keep in mind that each word is further converted to 3 parts, like 3 attributes associated with it. And now let's look at this 2 here. This 2 now, it queries its left 2 words in the context. What does it do? What does it want to query about? It wants to ask its left context, like the words before it. He wants to ask this word I and went about how they attend to it. Or you can think of it in this way: how much similarity do they share? So basically, when you query, like this Q3 queries this K1, this word 1, it will query this word's key, that's key 1. So Q3 and K1, it will be computed into an attention weight, and this attention weight is represented by alpha 1,3. So alpha 1,3 means the attention score that the word at position 1 will attend to the word at position 3. And now we have a value of 0.2 as this attention weight. This is essentially how I will attend to 2, or like how I is similar to 2. And similarly, we can compute alpha 2,3, which is 0.1, for how went attend to 2. And so on and so forth. We will get each attention weight or attention score from each context position to the current query token 2. That is alpha 1,3 all the way to alpha 5,3 and including itself alpha 3,3. And then we will get the new, better representation for the token 2. That is the Y3. The Y3 will be the weighted sum of the values of each token. That is the sum of alpha 1,3 times V1 plus alpha 2,3 times V2 plus all the way up to alpha 5,3 times V5. And in this way, you can represent each word through this self-attention. So self-attention basically means that you attend to your context words, to anything from your context, from yourself. And here's more details on the computation side. You can go through this in your free time, but let's just keep the big ideas in mind this time. Right, so for that, we only talk about a single head. But in transformers, we all know that's multi-head attention. Like we have this multi-head in encoder and two other multi-head from decoder. So what is multi-head? So multi-head basically means several heads in parallel. And in real computations, we just simply concatenate all heads output. For example, in BERT, for each layer in BERT-based model, we have 12 self-attention heads, and each self-attention heads will generate an output of 64 dimension. And this 64-dimensional vector times 12 become the final 768 dimensional vector for your layer output. And as you can see, in encoder, we have multi-head self-attention. And in decoder, we have this mask multi-head self-attention. Simply put, the mask is needed because in decoder, you can't see the words in the future. Basically, you can't see your context to your right. So you need to mask out anything from your right. And in the top, we have this encoder-decoder multi-head self-attention. This is specific for transformer architecture. In GPT, we don't have encoder-decoder multi-head self-attention. We will go into that. And essentially, why do we need multi-head? From my understanding, some heads may be more expressive than the others. And multi-head helps capture a more nuanced understanding of the input sequence by attending to multiple parts simultaneously. And because transformers use multi-heads in parallel, where each head can potentially capture a completely different word-word relation. As you can imagine, some heads may capture some relation between your current token and some context token, but some other heads may have a different opinion. And if we can combine all of them together, we can get a better representation for the current token. Right, and now let's just talk about the masked multi-head attention. So in the standard transformer, the target sequence is provided to the decoder only once. So the purpose of the masking is to make sure that the states do not attend to tokens that in the future, but only to those in the past. So the mask looks like this. So queries are on the vertical axis, keys and values on the horizontal axis. This means that for generating the first token, you cannot attend to anything. Or maybe you can attend to the very beginning special token, like beginning of a sequence, or you may have saw that before. You may have seen that before. And when you're generating the second token, you can attend to the states of the first token, and so on and forth. So this is to give you an idea. Right. And this is our GPT-like models. GPT-like models are transformer decoders, as you can see on the right. So it still applies the causal language modeling. So language modeling is basically, to my understanding, a conditional probability model. So given the first several words, you predict the next. And given this word, you predict the next, so on and forth. So at each time step, you have those words before you. So that's the causal language modeling. Basically, it looks to the left tokens, and no right or future tokens are considered for context. And there's no encoder-decoder multi-head self-attention because there's no encoder. And input text is directly fed into the decoder without being transformed into a higher, more abstract encoder representations. Why decoder only? It is more efficient language modeling, and it generates outputs more quickly. And how do we decode exactly? I just want to mention that this decoding process, in the next few slides, I'm basically focusing on the inference time decoding. That is, for the next few slides, I will talk about temperature, top case sampling. These are not used in your pre-training. This is just for give you a sense how you actually generate your output. So when your model are decoding, at each time t, you have your context tokens up to time t minus 1. And just to mention that the starting context token is usually a special token signaling the beginning of a sequence, like this special token here. And your input will be your text and positional embedding, like like in the transformer. And suppose the input context tokens are represented by U, and embedding matrix WE, position embedding WP. And now you will have your first input to the first subsequent transformer block, which is H0. This H0 is U multiplied by WE plus WP. And this hidden state input will go through all this self-attention, layer norm, and all the other operations, and you will get an output like after your transformer block. And this will be your H1, and H1 will go through this thing, and then the output will be further fed into your next transformer block, and so on and so forth. You will get your final output like Hn at the end of this all 12 transformer blocks as an instance. So your final target token distribution will be basically the submax of Hn times your output embedding matrix, WE, here. So and keep in mind, this is the output probability matrix, output probability distribution for your input token, lowercase u. And of course you want maybe the argmax of the submax to be the correct index for your next token, right? So this is how we do language modeling. Like we do language modeling to predict the next word. So given the current word and its context, we want to predict the next. So this is how this output distribution is generated and what is represented. So this is the submax score in the math equation. That is the output probabilities for token X and time I. But let's suppose this. So if I inference time, you just do greedy decoding. That is, you just output the highest probable token at each time step. For example, at time I, you just output the very argmax of your submax probability. Then this will give you the suboptimal sequence in most cases. For example, suppose your context is try this cake, I baked it myself. And the optimal response will be this cake tastes great as a completion rate. But in your actual generated response, in the first at time 1, this is generated according to the highest probability. And then is followed because is a higher probable token compared to cake. And OK might be also a the highest probability in the output probabilities for token X. So your generated response will be this is OK, and this is not what you expect, right? So you may consider more than just the highest probability token as the next word. And to achieve this, we can use some strategies, including temperature and top P sampling. Let's talk about temperature. So temperature is, the use of temperature is to increase the number of words that you will be considering for your next word. That's random sampling with temperature. So compared to the original submax, you just scale the output distribution in this way, that you divided your each token your output your target distribution by T, by the temperature. So the temperature is used to increase the probability of probable tokens while reducing the one that's not. And to see this, you can think of it in that way. Like, you can see this figure here. So comparing temperature 1 to temperature 0.5, like a higher temperature, for higher temperature, you will have like more tokens that will give you a somewhat high probability that you may want to sample from. But for lower temperature, like only those words that with very high probabilities are more likely to be sampled. So that is to say, the higher temperature, you can get more diverse outputs. And for another strategy, we can try top P sampling. Top P sampling, or the nucleus sampling, computes the cumulative probability distribution and cut off as soon as that distribution exceeds the value of top P. So this basically means that you have, this is again to increase your probable tokens to be sampled from. So let's suppose that you have a few words which their cumulative probability has achieved some top P value, let's say 0.25. And to exceed this 0.25, you may just need a few words to achieve this, right? Because you're computing the cumulative probability. But if you have a higher top P value, you may need more words with all their probabilities, and you can have that pass your preset P value. And this equation here is essentially how you do with top P sampling. So in other words, the higher top P values can produce less repetitive text, since at each time step, more word types are included in the sampling process. And your probabilities, this capital P, or your word probabilities are given by your GPT model. This is how you compute your cumulative probability distribution. Again, the idea for this is to get more diverse outputs because you don't want to fall into a suboptimal sequence. All right, now let's talk about pre-training. In the pre-training stage, it's doing causal language modeling, as I mentioned. And for your input to your pre-training, you always have a batch of sequences or a batch of sentences that's randomly sampled from your training corpus. Let's say now we have this training batch of shape BT, where B is your batch size. So basically we have 4 sentences in our batch, and each sentence contains 10 tokens. Suppose now we're looking at this green token, and this is our current token, and we have seen its context to the left, which are shown in yellow. And our pre-training objective is to predict the red token. And we want whatever input before this red token will generate the correct index for the red token. That is our training objective. So basically we want our model to give the correct index for the label as 513. And for training, we will do multiple iterations. Like you can see for this Shakespeare's training data, at first it's just not readable, and then after 250 iterations, it becomes something that seems to be worse, but we can't really decipher that. And after more iterations, like after 30K iterations of training, of God that breathes forth thou must like the stars. So this already looks very much like Shakespeare's writing. So you predict what comes next, and you sample from that distribution, and then you feed that back to the training process. And as you train your GPT longer and longer, the output text becomes more coherent and consistent. So here, just for a brief recap, so this is the loss function for the causal language modeling. So let's just keep in mind that causal language modeling is self-supervised learning. So basically, self-supervised learning means that you don't have external annotations or labels. So you use words in your sentence itself to serve as your target, to supervise you during the causal language modeling training. So this next token prediction objective, or namely the CLM loss, is the cross entropy loss defined by the the sum of log probability of this. We will just read it here. Right, and on the training curve, for example, for this toy GPT-2 and Llama, you can see that more steps and more tokens and larger models. For more steps, more tokens, larger models, we will get lower loss. And here are some powerful pre-trained base models. So base models are basically pre-trained models without any further supervised fine-tuning or even RLHF steps. So base models can already learn powerful general responses, and they are just pre-trained on a large unsupervised dataset. To be used for the downstream tasks, you can add some further layers or any architecture that you want to be used for your classification tasks, your entailment, similarity, and multiple choice, and many other downstream tasks. And two base model examples, GPT-3 and Llama. You can compare them. And one thing to know is that base models can be prompted directly. So you may not know what is prompting. So prompting is basically directly ask your language model to give you an answer. So you prompt your model with a prompt, and it will generate an output as a response. So make your model look like a document. And for example, you can give your model a short instruction followed by your real question. And what is meant by instruction, that you maybe have your description here, and you wanna ask this question: how old is this guy? And you give the answer as 54. And now you ask your real question of where does she live? And you put this completion trigger here as A. And then this model will be tricked into performing a task by completing the document. So essentially, after GPT-2, more prompting methods are seen in different papers or like just on the web. So prompting seems to be the new trend over fine-tuning, like traditional fine-tuning. Here I mean traditional fine-tuning. So how do you design your prompt? So this is something related to prompt engineering. So prompt, field shot, especially field shot prompt, will be several example input and output pairs, or query prompt and response pairs that are given as instructions and followed by your query input. And you can also do chain of thought prompting. We will talk about it later. And what makes a good prompt? I want to share with you this slide I found from Princeton's this course lecture slides. I think this is really this is a good description of what is a good prompt. So a good prompt is one that is general enough to be used for a variety of tasks, but specific enough to be helpful for a particular task. But to achieve this, we may need some experience. So we may learn how to write good prompts through our learning experiences. And just to add a little about the comparisons between few-shot prompting and prompt-based fine-tuning and head-based fine-tuning. So head-based fine-tuning is just the traditional fine-tuning, the standard classical fine-tuning that we used before. That is, we fine-tune, we add the CLS token and we fine-tune it for our, for example, the sentiment classification task. Here our input will be no reason to watch. I think this is a movie review, right? So for this movie review, we want our model to identify its sentiment as negative. So during fine-tuning on the movie review dataset, we fine-tune the CLS head, and we get that as our binary label for positive and negative. And for prompt-based fine-tuning, prompt-based fine-tuning is still fine-tuning. But the difference is that if formatted the input as a prompt, it will predict a word which will then be mapped to your output label. For example, here, no reason to watch will be accompanied by a short prompt or a template. It was mask, and the mask will be the word to be predicted by our language model. And the reason to use prompt-based fine-tuning is because prompt-based fine-tuning is more similar to the task of the pre-training task, right? Like for pre-training tasks, we're like for BERT, especially for BERT, we're using mask language modeling, right? And if we do it if we fine-tune it in a similar way, we will get better performance. That's just the intuition. And then this word will be mapped, this predicted word will be fine-tuned, and the output prediction will be mapped to, for example, the output will be a word great or terrible, and then it will be mapped to a label. But for few-shot prompting, there's no gradient updates. I want to say that base models are not the system models. So base models like the pre-trained models like GPT-3 or Llama are intended to complete documents, no interactions with users. But pre-training shouldn't just be the limit. The model can be further fine-tuned. So now let's go into the second stage, supervised fine-tuning. So before that, let's talk about assistant LLM training in a nutshell. So the training process does not stop at pre-training for system models or for the chat models. And for the actual assistant models, we have a supervised fine-tuned models. We have the supervised fine-tuned models which can be further fine-tuned through reinforcement learning from human feedback, or LHF, to mimic human responses through reward modeling and reinforcement fine-tuning via the PPO frame. So LHF process often involves multiple iterations of fine-tuning and data collection with human feedback. Here's an example of the training process for system models. This is taken from the recent Llama 2 paper. I think this is a great illustration of the training process for like open source LLM like Llama 2 or even GPT. So we always start with pre-training, and we have our self-supervised learned model. For example, here we have this Llama 2 pre-trained model, and then we do supervised fine-tuning. Again, the supervised fine-tuning will be using some demonstrations collected from your contractors. That is low quantity, high quality data. and you still apply the causal language modeling objective on this data to get the supervised fine-tuned model. And then we still want it to be further mimicking human preference. So but we can't afford to have a human sitting in the loop to tell us this response is good, this response is bad. We can't afford that. So we need instead a proxy of human feedback, which is our reward model, to tell us the reward score for our response. And then reward score will be the guidance for our PPO, reinforcement learning, to get better policy. A policy is essentially a language model. Basically, we will use the reward given by the reward model to guide this reinforcement learning to get better chat models. And this is how we get our chat models, because we are mimicking the human preference of your input prompt and your desired response from this interactive chat. And for ChatGPT Assistant, this is the whole pipeline. Right, for pre-training, we have talked about, and for supervised fine-tuning, let's talk about supervised fine-tuning. So supervised fine-tuning starts with collecting demonstrations from people or contractors, and this low quantity, high quality, we just need around 10 to 100K prompt response pairs written by the contractors to be served as our training data for the supervised fine-tuning stage. And the language model will be initialized from our base model, the pre-trained model. And then we fine-tune this pre-trained model on the demonstrations towards the language modeling, that is next token prediction objective, and we'll get our SFT model. So for demonstrations, here's an illustration I taken from this paper that will give you some sense of what is instruction. So instruction is like, please answer the following question. What's the boiling point of nitrogen? Or you can use chain of thought fine-tuning, answer the following question by reasoning step by step. And you give your query, and you walk through it step by step to let the language model generate a similar response according to your instruction. This is called instruction following fine-tuning or instruction tuning. Right, so language modeling. One thing I want to share with you is that for instruction fine-tuning, since our input will be prompt and response pairs, and we are optimized for the next token prediction objective. So what tokens are to be considered in our prediction, right? In our prediction objective, because we now don't just have any raw text, we have a prompt and response. So there could be both ways. The first one is just predict next word in your prompt and response. So you basically consider every word in your prompt and response as your target word, and you wanna predict every word as your target during the instruction tuning. And you can also just consider the token in your response, and basically you just zero out any loss for your prompt words. That is, you predict the next word in the response only. And just to clarify, things used during inference but not during training stages for ChatGPT, as I've already mentioned some slides ago, the decoding strategy like top P sampling is employed during inference time to improve LLM answers. So that's not used during pre-training. Alright, so now let's get to the exciting part, part 3, RLHF, reward modeling and reinforcement learning from human feedback. Okay, so first we need to get this reward model, the reward modeling. And reward model is just, as I said, a proxy of human feedback that we just want it to serve as a surrogate for human feedback to give responses a score scores. Right. So for reward modeling training, so we need to train a reward model. The idea is very simple. So for example, you have 3 completions in yellow. You have completion 1 or response 1, response 2, response 3 for the given same prompt. And you find that according to your human experience, you find that the first response is good. So you want to assign a high reward score. You want to score it higher. So you want to give it a score of 1.2. And for example, your second response is no good. You don't like it. You want to discourage it. So you give it minus 0.5. And for the third one, it's just okay. So you want your model to be according to your human experience, human preference. And to learn this model, you just need a loss function that measures the predicted rewards consistency with the labeled ordering. The label ordering is just, for example, the first one is better than the second, and the second one is worse than the third, and the first one is better than the third. This pairwise comparison. We will go into it in the next slide. And here's some general illustration for how you train your reward model. So suppose now we already have our supervised train model, that is our SFT model, and you can query your SFT ChatGPT given your request, and you can generate alternative responses A, B, C, D, and you let the human agent to give you his or her judgments about the response ranking in a pairwise comparison way. So keep in mind that we need pairwise comparison because it's always easier to discriminate between 2 responses, right? And then the reward model is trained via a binary classification training objective, or the binary ranking loss. Then we use this reward model to automatically compute reward score for any response. That will be used later in the PPO stage. Here's a great illustration for how we actually train our reward model. So we collect human feedback for our different pairs of responses. Suppose we have this response J and response K. And now we let the human sit here and judge which one's better. Suppose this human thinks J is better than K. Now keep in mind, this will be our goal, our target, that this pair of responses, J is better than K. So we want our model to give a reward for J, RJ, and a reward for K, RK, which will signal this judgment. So we always want RJ to be larger than RK. To let the model achieve this, we define this log sigmoid loss. This loss follows from the Bradley-Terry model for pairwise preferences. It means that if RJ is larger than RK, the loss is minimum, right? When RJ is very large and RK is small, then you will get a very low value for the minus log sigmoid as your loss function. So you minimize, when you train your reward model, you minimize your loss, and this will give you the targeted behavior of the model. So just to add that since you are minimizing the loss between each pair of output reward scores and human preferences, you have every pair from your data set of human judgments, and this is how the loss is officially defined. Right, so that's just a brief idea for reward modeling. And we can go into more details when I talk about the llama training. Let's now just look at reinforcement learning. So again, after we have our reward model, we can use that reward to guide our reinforcement learning to get better SFT model. So this RL model will be, again, trained using prompts written by contractors. So that's, again, low quantity, high quality. And this is a pipeline taken from a paper this year to show how you do your PPO training. And just to know that you can add this KL divergence term to your PPO learning. And this KL divergence term is essentially used to discourage a high difference between the RL policy and the SFT's fine-tuning. So you don't want your SFT model to be very different after you apply reinforcement learning. So here's the final reward function for your reinforcement learning, your PPO. So for PPO framework, I will not go into details, but just keep in mind that we just use this reward to guide the learning of a better policy. And this policy is just your language model. So we have our reward, which is defined just now by our reward model, given by our reward model. And we have this KL divergence term, which is just to discourage the difference between your initial supervised model and your later learned policies. Right, so for reinforcement learning, reinforcement learning, the training, it's actually, the idea is just to encourage the answer you want and discourage the answer you don't want. And this scores, this encouragement or discouragements are guided by your reward model. So why RLHF? This is a very good question. And since you have noticed that we use binary comparisons to let the human agent to generate a preference between pairs of responses. Why do we do that? Because it's always easier to discriminate one over another than to create one. So you can see that it's always hard for a human annotator to give you some response. But it's much easier to discriminate which one's better. And performance-wise, using RLHF works better. As you can see, this red and orange lines denote a higher performance, which are using PPO. And the green one is SFT model, and the blue ones are the base models. So you can see that RLHF models works better, have higher win rate against the SFT model. And SFT or RLHF models actually lose entropy because they are mimicking human preferences. They may be like a little too, sometimes a little rigid in generating an answer according to your preference. So maybe sometimes when you ask the model multiple times, like in ChatGPT, like at first time you think the answer is good, but not very good, you ask again, then it will just give you some answer that makes you feel that the model seems to sense that you don't like the previous answer, so it gives you something else. But in fact, you may just want it to expand the original answer into like more explanations. And if you continue that prompting with the same query, same question, the model will just keep saying like the not so related answer. So I guess this could be caused by like the model loses entropy. So in other words, the RLHF models might confidently output very few variations, but base models can be better at tasks that require diverse outputs. And here are some human text generation comparisons with LLM text generation. And for a chain of thought, you can use a few instructions to let the model think step by step. And here I just give you some intuitions. Like for standard prompting, in this example, the model input would be your question, like Roger has 5 tennis balls, he buys 2 more cans of tennis balls, and each can has 3 tennis balls. How many tennis balls does he have now? The answer is 11. And you ask another question and waiting for the answer. This question is, the cafeteria had 23 apples. If they used 20 to make lunch and bought 6 more, how many apples do they have? The answer is 27, which is wrong. But if you use chain of thought prompting, that in your given instruction answer, you say something like, Roger started with 5 balls and 2 cans of 3 tennis balls, each is 6 tennis balls. 5 plus 6 equals 11, so the answer is 11. And then for your actual question, the model will generate a similar reasoning process. And by saying, the cafeteria had 23 apples originally. They used 20 to make lunch, so they had 23 minus 20 equals 3. They bought 6 more, so they now have 3 plus 6 equals 9. The answer is 9. Now the answer is correct. This demonstrates the effectiveness of chain of thought prompting. There are more variants of chain of thought prompting, like zero-shot prompting, zero-shot chain of thought. So by zero-shot, you just simply in your answer trigger word, after that you just add this simple sentence, let's think step by step. But it doesn't always give you your expected output. And you also have plan and solve prompting and answer extraction prompting. I will not go into details. Right, and here are more examples from the Microsoft Build slides of few-shot and zero-shot prompting. Here's just some additional notes on Automatic Prompt Engineer, or APE, zero-shot COT trigger prompts. This just to say that APE can work better than human-designed zero-shot COT trigger prompts. For example, let's think step by step is our well-known, our famous COT prompt, trigger prompt, right? But in fact, by APE, we have something like, let's work this out in a step-by-step way to be sure we have the right answer, and the accuracy will become higher in this example task. And there are also retrieval-based LLMs, retrieval-augmented LLMs. For example, you might heard about Llama Index, the index things you may be interested about. Oh, and this is some interesting thing, ensemble. So we have, since you can get unlucky, or your model can get unlucky sometimes, and sample a bad thought, that for the same prompt, you can do it multiple times. You can prompt with the same question multiple times. For example, here, you prompted 3 times and you have 3 different answers. And you can then do some aggregation, like voting, majority voting, or similar strategies to get your final outputs. So here, maybe you just marginalize out the reasoning paths and aggregate the final answers. So two answers will be 18 and 1 will be 16. Then your final answer will be 18. So this is to give you a more accurate result. And an interesting thing I want to mention here is the rumors about GPT-4 using mixture of experts. So some hacker mentioned that GPT-4 is 8 MOE, and this person from Meta has also shared some similar thinking about the MOE and GPT-4. So I just wanna just give you a hint what MOE is. So different from ensemble, in MOE only one or a few expert models will be run. think about it in this way. So we have this input text X. We have three essentially same identical expert models. Let's say expert 1, expert 2, and expert 3, and a gating network. This gating network will basically generate a 0, 1 number or like other number indicator to be used to signal which expert model will be used. Like not all of them will be activated. This is the gating, right? So gate will let you know which one will be used and which one will not. And so here this GIX will be sum to 1. Essentially it means that some will be chosen and some will be not. And your final output will be generated using some of the experts that is chosen by your gating network according to your input. And there are also constraint prompting. You can enforcing logical control in your prompting. And talking about more accessible fine-tuning, we can always fine-tune a large language model, right? But it's very costly, and we don't always have those equipment and computing resources as large companies do. But we can still achieve that. We can do it through PEFT, parameter efficient fine-tuning, like you might have heard about LoRa, and other low precision inference like bits and bytes. And later we will talk about the Llama model, which is which uses which is open source, and you can do some fine-tuning on that. As for cheaper fine-tuning for PEFT, it is essentially efficient fine-tuning via low-rank adapters. So for rank, let's just think about dimension. So the key idea is that language models can still perform well if we convert the parameters to a lower dimension. So that's the whole idea of PEFT or LoRa. I've taken the slides from this great language model tutorial from AACL last year, and I encourage all of you to read through it. And now I just use their slides to share with you my thoughts on what LoRa does. So for LoRa, low rank adaptation of large language models, we add this small adapter, this LoRa adapter, in the feed-forward module. And if we zoom in on that adapters, you can see that we have these two little things here. The lower one will convert from higher dimension to lower dimension, and then the upper one will convert from the lower dimension back to the higher dimension. So this adapter will be added to your original pre-trained architecture. So essentially, in your fine-tuning, you will keep the pre-trained weights as they are, and you just train the adapter. That is the two little things here. And keep in mind that this rank, this dimension will be lower than your dimension for your feed-forward or your model. Thus, you can see that this rank R or this dimension R is much smaller than your model's original input dimension, right? The D model or DFFW. And your final output for this feed-forward layer, your H prime, will be H plus delta H. So this is actually the gradient update, but with the actual gradient replaced by the delta H computed by your adapter. So as I said, the motivation for LoRa is that downstream fine-tunings can have lower intrinsic dimension than your pre-trained weight. And the weight after fine-tuning, W will be W0 plus the updates to the weight. And we just use this B and A to replace the delta W, where the rank R of B and A are much smaller than the minimum of DFFW and D model. So after that, we have our fine-tuned weight equals to W0 plus plus BA. In other words, all downstream tasks share the PLM. The LoRa in each layer and the classifier heads are the task-specific modules. And besides LoRa, we have a further quantized version called QLoRa. So that's, again, further quantized. So for LoRa, you have 16-bit. For QLoRa, we have 4-bit transformer. And one last thing, for ChatGPT. ChatGPT has great API access, so you can always use it for your own interest or research or anything else. All right, now let's talk about more large language models. First of all, let's talk about Llama. So Llama is an open source large language model by Meta. And in terms of open source, it still has some restrictions, so it's licensed under this Llama 2 community license. So the architecture of Llama is shown on the right, which is taken from this Zhihu site, and features smaller models and more tokens. The difference from its earlier counterparts is that, as I list here, it normalized before going into the transformers. So pre-normalizing RMS norm before the input. And other things are pretty similar to the decoder's architecture of ChatGPT or transformer. And it uses rotary embeddings and uses this different silo activation function. So Llama 2 emphasizes on safety. So Llama 2 is just released this year after Llama 1. And Llama 2 and Llama 2 Chat are both released. So Llama 2 features a series of chat-like assistant models. So as the paper has emphasized a lot on safety, here this figure just shows that compared to other models like Vicuna or Palm or ChatGPT, Llama 2 has lower violation rates, indicating that they are safer. So let me just walk through this introduction to Llama 2 because I wanna just give you more hints of large language model training that is very similar to ChatGPT. But since ChatGPT is not open sourced, let's just talk about some open source models to understand a bit more about large language model training. First of all, let me share with you this great chatbot arena leaderboard for large language models. So is Llama 2 a better base and assistant model? Let's take a look at this board. As you can see, the top one is still GPT-4, and on the chart you have Vicuna, 33B. And then we see Llama 2 70B chat, which achieves an impressive MMOU score, which is language understanding score of 68.9. This is already very good. And its MT bench score and L rating is not given. MT bench score is also high. Now let me just talk briefly about Llama 2 pre-training. So for Llama 2 pre-training, it uses 2 trillion tokens from publicly available sources and increases the context length to 4K and uses group query attention to save cache size. Just a little bit about the GQA, the group query attention. So in ChatGPT or the original transformer, we just use multi-head attention, where you can imagine that for each head, for each query, we have this key and value, right? But like in group query, every two query can share, or every several query can share the same key and value. So that could save some cache size. I'm not very familiar with how this is efficient computing in terms of the source allocation, resource allocation. But let me just go through this GitHub issue that helped me understand a little bit more about this GQA computation. So GQA reduces cache sizes for keys and values by n has divided by nkv has times. So n has is your actual local, the number of your actual local has, and nkv has will be here your shared, your number of shared has. For example, your original local has, here you have 8 original local has, and you only have 4 kv has. So that saves the cache size by 2. Because they have reduced sizes, they're later needed to be pulled back to the actual size. And this is simply done by repeating, as you can see from the llama model.py code from the official website, official GitHub. So for an example, suppose you have your input in the shape x in the shape 1, 2, 3, 4, where 1 is your batch size, 2 is your sequence length, 3 is the number your kv has, and 4 is just your head dimension. And now after you do your group query attention, you need to put it back. You simply do it by repeating the third dimension. So you basically times the number of repetitions, like here we time 2. And we simply will have the repeated vectors in the third dimension. And in terms of computation and performance, GQA doesn't hurt the performance compared to multi-head attention, and it gives you higher throughputs. So I guess that's why GQA is used for Llama 2. And here are more pre-training model configurations for Llama 2 70 Hugging Face models. As you can see, the vocab size is 32K, and the hidden size, dimension size is around A192, and you can also take a look. And Llama 2 models outperform Llama 1 models on various benchmark tasks, including coding, common sense reasoning, world knowledge, reading comprehension, math, MMOU, BBH, AGI eval. The last 3 are all like language model understanding benchmarks. So so as you can see, it is evaluated against like complex and hard tasks. So just a little side notes on the LLM benchmarks. Like for MMOU, it's a multiple choice test set featuring test prompts of question followed by 4 choices and the trigger prompt correct answer. And you prompt your language model with this test prompt, and you get your answer, and you correct your accuracy with your ground truth answers. And BBH, Big Bench Hard, is a challenging benchmark encompassing various test scenarios. And this Big Bench Hard, not only does it support the standard answer-only prompting, it also asks for chain of thought prompting, so it's a pretty hard benchmark. And AGI eval, this is a benchmark focusing on human-centric benchmark. It features data from like exams, including the Chinese Gaokao and the US SAT and GRE GMAT and similar things. So for Llama, that's all for the pre-training. And for Llama 2, supervised fine-tuning. So Llama 2 does supervised fine-tuning on more than 27K annotations. So this high quality data, high quality examples. But the SFT data is not publicly available. And again, for training, it employs the causal language modeling objective and zero out the loss on tokens from the user prompt. In other words, it backpropagates only on the answer tokens. And here's the reminder for the CLM loss. As for safety measures, since Llama 2 emphasizes a lot on safety measures, it uses various methods to ensure safety, including adding a safety pre-prompt to generate your supervised fine-tuning data, and also in your inference. For example, you can add this pre-prompt of "you are a safe and responsible assistant," and then fine-tune the model on the safer responses without the pre-prompt. So this essentially distills the safety pre-prompt context into the model. And for reward modeling, we don't just have one reward model. We have a safety reward model and a helpfulness reward model. And then during RLHF, we set safety threshold. And here's an example pre-prompt taken from Llama inference, the Llama generation.py, which is used during inference. Like this system, default system pre-prompt consists of this interesting sentence of "you are a helpful, respectful, and honest assistant. Always answer as helpfully as possible while being safe." And here are some example abstractions for how you define your datasets, your like safety preference dataset, where you need to add this "is safe" label to indicate where your prompt is safe. And you can, if you want to do similar things, you can refer to maybe this abstraction. And for Llama 2 chat model, for this Llama 2 assistant, we need to train our reward model. So different from ChatGPT and other counterparts, the reward model for Llama 2 is made using chat model with classification head for the auto-regressive next token prediction replaced by a regression head for scalar reward prediction. Again, this is followed, the reward modeling uses binary ranking loss. And here's a better explanation of how this binary ranking loss actually works. So for the same prompt, let's say we have response 1 and response 2. And given response 1 is better than response 2, we want our reward model to know that. So, for example, our reward model will generate, for this given prompt and response 1, it will generate a score 1. And for prompt and response 2, the reward model will generate score 2. And score 1 indicates chosen, and score 2 indicates reject. And our binary ranking objective is just maximizing the log probability of chosen larger than reject. And this probability of chosen larger than reject will be further written into the sigmoid function of score 1 minus score 2. You can go through the steps. Which means that we want to maximize this. Or let's say, now let's think about it more closely. That if we add this margin to score 2, to achieve the same goal of maximizing this log probability, we need an even higher score 1 to achieve this, right? So in other words, by adding this margin, it will encourage a more diverse score 1 and score 2, or essentially a more diverse response 1 and response 2. That is to encourage significantly different response 1 and response 2, right? This idea is essentially used in the Llama 2's ranking loss. The Llama 2's reward modeling features this ranking loss of the binary ranking loss minus the preference rating term, like the margin term. So it further pushes for a larger difference between the chosen and the rejected responses, encouraging more distinct responses. And if you're curious how this preference rating is defined, it is actually given during the human annotators, during the human annotation collection. So alongside your comparison for the given pairs, the human annotations are also asked to give preference ratings, like if this response J is significantly better than response K, or better, or slightly better, or negligibly better, or unsure. And we train two reward models because the helpfulness and safety sometimes trade off. So let's say we have a helpfulness model, reward model RH, and safety reward model RS. And here are just how you assign your preference rating, the MR function. So given you R, your rating, you have this discrete function MR signaling the margin. And on those responses that are that one is significantly better than the other, the margin helps a little, but still it is helpful. And here are the results on the helpfulness and safety data test set, the meta safety, meta helpful, and you can see that this safety you can just see the results of using the safety RM and helpfulness RM are better than not using on the test set. And here, another thing that's different from ChatGPT is the RLHF stage of Llama, where Llama uses rejection sampling to sample any responses for a given prompt, and the best response for that given prompt is then chosen and is used for the next iteration of supervised fine-tuning. The idea is that when you sample more from the same given prompt, you can see that this orange area basically indicates the potential of using the potential gain with rejection sampling. Let me put it this way. So you have your let's say when you have more samples, you have a sample with your max reward, and you have the median of all responses, the median reward score of all your responses, and you can see that as n goes up, the max of the rewards, it can be a lot higher than the median of the rewards, indicating that you are sampling a better response, like a response with a higher reward, and you want that to be used for your next iteration of SFT, right? So that's how and why that's why rejection sampling is used. So rejection sampling may bring out the better response. And again, we fine-tune Llama 2 chat model with PPO. And again, here the final reward function for PPO is your reward function by your reward model, and minus this beta and KL divergence term. And for this reward model, reward score is chosen from either the safety reward model or the helpfulness reward model. So when your safety reward score is already below some threshold, or if your prompt is about safety, then you need to use your safety model. And again, here are some other things. So it's not the score that's directly used, it's actually the logic before the score that is used and is whitened. And other things to note for Llama 2 chat RLHF is that rejection sampling fine-tuning was performed only with the largest 70B Llama 2 chat models, and all smaller models are fine-tuned on the rejection sample data from the large model. Essentially, they are distilling the large large models' capabilities into the smaller ones. And ghost attention is used to help with monitor consistency. And the authors of the Llama 2 paper seem to suggest that RLHF is crucial to the model's creative writing abilities. This could be a little different from what we have heard before, but let's just keep that in mind. And here are more comparison results. I will just quickly go through them. And one thing I want to point out is that even though Llama 2 outperforms Llama 1, but Llama 2 chat doesn't really have a very better performance on coding. So maybe the model does not work very well with coding. And moving forward, we have this baby Llama 2 training from scratch that you can, with which you can deploy your model in C. And I've tried this Llama 2 C to run some text generation. And on my laptop, this model runs around 56 tokens per second, just to give you some intuition about it. And here are more fine-tuning resources. Right, so that's a lot about Llama. Now let's talk about Vicuna. So Vicuna is created by FastChat. It's non-commercial but open source. The training code and models are all open source. And it's instruction fine-tuned chat model, and the base model uses Llama. So here's the Vicuna workflow. So you collect data from user-shared conversations from sharegpt.com, and you do supervised instruction fine-tuning on Llama with that data, and then you do distributed serving with FastChat, and you access the outputs. You assess the outputs with GPT-4 using LLM as judge, And Vicuna is trained with PyTorch FSDP on 8 A100 GPUs in just one day. So here's the training details of Vicuna model. And the main takeaway is that Vicuna is instruction fine-tuned Llama-based models on around 70K user-shared conversations collected from sharegpt.com. And let's again take a look at the chat arena leaderboard. So Vicuna performances are very good, especially on the yellow rating and the EMT bench. On the MMU understanding, it's not as good as the other models like GPT-4 and Right. So that's for Vicuna. And now let's just very quickly go through the PaLM, the path-based language model. So the PaLM models are actually an efficiently trained large language model, still using decoder-only transformer model, but it features training on 6,154 TPU V4 pods. And their light-weighted models, the Gecko option, are suitable for mobile devices. And they have released PaLM 1 and PaLM 2. PaLM 2 is released recently. So the pathway system enables highly efficient training across multiple TPU pods. Since I'm not an expert on this training, efficient training, so I'll just leave it for your own research. Right, so I want to introduce you the FLAN-PaLM. So FLAN-PaLM is just instruction fine-tuned PaLM on the FLAN dataset. The FLAN dataset encompasses input pairs of prompt and responses that are formatted via instruction templates. So FLAN dataset is an instruction dataset. And the FLAN dataset contains more than 1,800 tasks and at least 20 instruction templates per task, like including 10 zero-shell templates, 10 field-shell templates. Fine-tuning on the FLAN dataset improves the model's ability to follow instructions and achieves better performance on unseen tasks. So FLAN-PaLM achieves very good multilingual and reasoning capabilities
and it's more compute efficient than PaLM. So for the instruction templates, so you basically transform some existing data sets into an instructional format. Like, for example, you have this entailment task, you have your premise, and you have your hypothesis, and you have your target entailment, now entailment, and you transform your input text by this template to make it look a little bit like formal, like you put in this document-like way. And here are the fine-tuning language tasks, the 1,836 language tasks from different, it spans across the tasks. And FlyPalm or PaLM have achieved good performances on the monotask language modeling benchmark, that is the MMOU. This is just right. The performance is just below GPT-4, so it's promising. It's already very good. And here on the Chatbot Arena leaderboard, PaLM Chat, the PaLM Chat model has also achieved good performance. Right. So for the last two parts, I will just very briefly go through the comparisons between large language models and domain-specific language models. So here I will just draw some comparisons between the models I just mentioned in this study sharing session. So there are Llama 2, Vicuna, ChatGPT, and PaLM 2. I compare between the pre-trained model, fine-tuning data, and whether they used human preference data collection, and what is the way for the comparison, and reward model training. And also whether their training code are available, and what are the evaluation metrics, and what's the training cost. And you can refer to these two pages for some intuition on the comparison between the different models. Right. Last but not least, more about domain-specific large language models. So the previous language models, the large language models, are general domain. But we have seen large language models in biomedical, chemical, cybersecurity, coding, and more domains. For example, for biomedical large language models, we have PaLM 2 by Google, BioGPT by Microsoft, and NVIDIA has also earlier released the BioMegatron. So BioMegatron, from what I know, is probably the largest large language model for biomedical LLMs. As for chemical LLMs, IBM has Moformer, and for cybersecurity LLMs, Google has PaLM 2. And for coding LLMs, you may have already heard about Codex or used it. That's by OpenAI. So what's next? What's next about the large language models? Or what's next about training? I think for me, the ultimate goal will be having better, faster, safer, and less biased large language models. And thank you. That's all for my sharing today. Again, this is my first time posting a study video or like a review of a deck of slides with my personal understandings and my thinking added to the deck of slides. I hope you like it, and if I say something wrong, please just let me know in the comments, and I will appreciate your likes. And don't forget to subscribe. Thank you. Bye.